Okay, so welcome to the follow-up to the display prep demo. And before we start, I do want to just kind of clarify and say again that I think that the display prep demo has sometimes been sort of unwittingly called into the so-called film versus digital debate, which to me is not really what this is about. It's about something bigger than that. It's about how we talk about and think about what a camera is, what a photographic look is, and how that final rendering of tones and colors and edges and everything else, how we can control that and author that as filmmakers. And so to jump in, the first thing I want to talk about is clarifying what I mentioned in the demo itself when I said when I talked about thinking of the camera as a data collection device. And I've heard some people a few times have sort of misunderstood that to mean I was saying to put the camera into some sort of mode where it shoots more magically raw imagery or something like that. And I'm not really talking about like changing a camera mode. I'm more talking about changing our thinking mode when we're shooting with a camera. And because the thing is, if you have a machine that's taking a recording, such as a camera that's taking 24 or some number of frames a second and a bunch of photo sites, a couple million photo sites within that are each getting a record, you're grabbing a piece of information about the scene that's coming in. And if you have a machine that does the same recording and it's a repeatable and reliable and dependable machine, that is a measurement, even if it's in strange units. And just to make an analogy, if you imagine that we have 3 rulers or tape measures, and let's say one of them is marked with meters and millimeters and centimeters, and one's marked with feet and inches, and one just has a bunch of crazy numbers on it they're all ascending, but they're not even evenly spaced or anything. If we have those 3 rulers, they're each going to do the same thing every time, and we can use any of them just as well. I mean, of course, if they're spaced too far apart, that's a different story. But just in terms of the units themselves, it doesn't matter. If you didn't know the conversion from meters to feet, you could put the meter ruler next to the feet ruler and see how many there are, and make an adjustment. And you could get the same result out of those 2 things. And even the crazy one, the crazometer, you could see where all the markings were on it. You could write it down. You could say this number 1 is this many millimeters, number 2 is that many millimeters. And even if somebody could take a survey of a site, and you're an architect and you're going to build on that site, you could do perfectly well with that. You just convert the crazometers into millimeters or meters, and you would have the result. And it's the same thing with imaging. And of course, there are multiple attributes of imaging, not just tone and color reproduction, but those are some of the absolute most important ones, and I'm going to talk most about those. And that's what I'm going to talk about now. I know there's other stuff too, but that really is some of the most important. And so what I mean by the machine doing the same thing is all of our professional cameras today are very reliable machines. It's 2019 right now. People know how to make machines that don't just randomly do different things every time. They actually do the same thing each time. This does not go for certain consumer stuff. This doesn't go for something like an iPhone camera because the software, not even necessarily the camera part of it, but the software is set to do all kinds of variable processing. It doesn't do fixed processing. It doesn't do the same thing every time. It does variable processing, so you don't know what the camera did. But all of our professional cameras, they really are repeatable. If you don't change the settings, it'll take a measurement to a fine enough degree that the margin of error is not really applicable to the look of cinema. So for example, this is the Alexa camera, and it's shown here in ARRI log C wide gamut RGB. So every time we point a camera, an Alexa, at a chart like this, or anything that's this color, let's say this gray patch here, which is close to middle gray, it's gonna, and we put the same amount of light on it, same color of light, and the object's the same color. The Alexa is going to make, see the numbers here? That's the red, green, and blue numbers. It's going to make 0.416416, basically 41. So it's going to do that every time. It's reliable and repeatable. And even if it wasn't, like as I said, this is in airy wide gamut RGB, but we could put it in, it doesn't matter, it could be in log C camera native, it could be in linear camera native, it could be in ACES. It doesn't matter because all of those things are unambiguously convertible from each other. You don't even have to figure it out. It's not like going from crazometers to millimeters. It's math that's built right in, like going from millimeters to inches. So the fact that this is in log C area wide gamut RGB is perfect. It would be perfectly applicable if we were instead in, let's say, log C camera native. We would just need to know that we were. So it's going to do the same thing every time. Here's something that's 5 stops under. You can see what number it's going to make when this amount of light in this color, or what if we go to 1 stop over and red patch? It's a pretty reliable machine. And so is film. Here's some film. Now, in this case of film, we actually have 2 cameras. This has been rephotographed because we shot it on film, and then we shot the film with a camera, which we call a scanner, but that's also a camera. But even though there's 2 cameras, we made both of them fixed and repeatable. Film is pretty reliable as long as it's processed correctly. There's probably a little bit more variation, just with the processing bath than there is with digital, but it's all so small that it's, again, for the purposes of an overall photographic look, the variance is completely, it's a tolerance that's totally acceptable. And then the same thing with the scanner, just like the film camera, we don't adjust the scanner. We get our settings, whatever it is for the show, for the project, and we know exactly what they are. And so you have 2 cameras that are fixed and repeatable instead of 1, but it's the same thing. You have a repeatable system. So every time, again, we put this amount of light onto the film and then onto the scanner, we're going to get the same result. So we're going to get the same result each time with that, and we're going to get the same result each time with this, but they're different, right? They look different. And let me just put a viewing LUT up. Right now we're viewing, these are log images. That means they're logarithmic encoding, but the projector is gamma decoding. So the reason it looks flat and milky is because we have a mismatch between something that's log encode and gamma decode. So let me just put my personal LUT on. That's for viewing it gamma, so that looks more correct on the screen. So you can see, and it just makes it easier to see the difference between them. So you can see, so each machine or set of machines it's gonna do the same thing each time, but it's not going to do the same thing as another machine. But we could think of that as one's in feet and one's in meters. And if you didn't know the conversion between feet and meters, we can just look that up. But if you didn't know, again, you could hold a meter stick next to a yardstick, and you could just see what the differences are. And we can literally do the same thing here. So when we compare, this one is area wide gamut, log C area wide gamut RGB. This one is 5219 scanned with the area scanner at some very specific settings. So we can make a conversion from between those 2 things, and you would do it literally the exact same way you would do with holding up your 2 rulers together. So we can say, for instance, we usually look at the green channel. When all you're thinking about is exposure, we usually look at green, and then you only look at red and blue when you're looking at color usually. So while we're looking at exposure and not color, you can see like this dark patch here, film is going to make the number 0.09, and the Alexa is going to make the number 0.099. And we can do that for everywhere on the scale, like this gray patch here. When film makes, that's film. When film makes 0.27, log C is going to make 0.14. And what we can do is we can make a conversion where you literally just tell the computer what those are. So like, you know, just now we said, is that right? -2. Yeah, so if we could go either direction, we can convert meters into feet or feet into meters. So let's just go towards log C. So that means when we have an input of the 0.27, we want an output of 0.14. So you can just 0.27 in is 0.14 out. And we can just go and do that for each spot on the chart. So I'm not going to make you watch me do that. But I've already done it. And that's right here. So, and I've done it for all 3 channels, not just green. We were just looking at green, but I've done it for all 3. So you get this slightly wavy transformation. If these were two digital cameras, it would be much closer to a straight line. Some of this is the idiosyncrasies of the film. But you can see that so we can just transform so that the same light on set, the same actual scene data, the original image data that was coming in through the lens before it was captured, we can push these into the same unit so that for whatever the density was in one, we make the other that. So I'm going to turn this on. This is a lookup that's going to follow this path here. And obviously it's slightly rough. I could have done it with even more points and gotten it more precise, but this is going to be pretty good. So hold on, let's just go back to, so this is what it looks like when I apply that, right? So that's with it off, and that's with it on. That's still in log. Let's look at it through a viewing transformation. So that's pushing it to be the same values. Now we're only doing density right now, which is, you know, exposure or, you know, tonal reproduction, not color reproduction. So we can see that if we compare that to Alexa, the grays are now going to match perfectly, but the colors still aren't quite right. So, oops, what do I have? Do I have something turned on here? No, that's right. Okay. So let's just actually hide the color so it's not popping as much. But you can see, so can you guys see when I'm going back and forth? Can you tell when I'm going back and forth? So you see down, so not only will you see the image pop, but down here you can see this is where the viewer is connected. And see when it, oops, as it goes back and forth, you guys see that? So anyway, so we can see now we have a matching tonal reproduction for each. You know, we can see like this is 0.43, or sorry, it's 0.45 on both, right? So we have matching tonal reproduction. So we've converted meters to feet in just for density, not colors. To do colors, you can't just do the 3 channels separately. Even though we did 3 channels, we did them separately. So that's called 1D. To get the colors to match, we have to do something that's 3D to push meters to feet. And you know, when I do something like you know, for a feature project or for the demo you just did, I usually do something a little bit complicated for that, but I'm just going to do a slightly simpler version. Oh, so by the way, so this is what we just did. That's the 1D. That's just the tonal reproduction. And now we need to do something that's 3-dimensional. And by 3-dimensional, I'm not talking about 3D movies. I'm not talking about stereo movies where you wear the 3D glasses and somebody jabs a spear at you and it comes out of the screen. I'm talking about math that's 3-dimensional math that uses vectors instead of scalars, which means it's coordinating 3 numbers together. So instead of 1 number in and 1 number out, it's 3 numbers in and 3 numbers out. And I'm going to do something that's not quite as complicated as what I do usually when I would build a transformation like this, but it's a little more complicated than what's used in a lot of transformations these days, like 3D LUTs and whatnot. And it's this little tool here that I wrote, which you can see all the code here for it. But I call it tetrahedral interpolation. I didn't invent the math for it. I just used existing math to make this implementation, and we can do that. which is something you can't do with the 1D math, because we actually aren't changing the tonal reproduction at all when we do this, because, let me just show you here, the gray, hold on, so if there's the whole cube, see we've got the 8 corners of the cube are red, green, blue, cyan, yellow, magenta, black, and white. So the line from black to white is the gray ramp of all of the possible colors, and it's in the very center, right? So it's here. Does that make sense? So what this thing is doing, as I do that to it, I haven't changed that gray ramp. See, we can look down the barrel of it. It's still a straight line, and it's still in the same place. If I just shrink this back down, that's still where it was before. So we've adjusted all the colors throughout the cube without adjusting the gray ramp in a specific way, which again, I'm not going to show it to you because it would be tedious, but just like I just did with the gray, where you can say this is the input number, that's the output number. So like I said, this is a little more complicated way to do it than is often done, but less complicated than I usually use. And if we bring that over here, so again, this is that's Alexa log C. There's our film scan. Both have the LUT on right now, the lookup to the viewing transformation on. The grays are the same, the colors are different. Now I'm going to apply that tetrahedral interpolation that I just did. See that? So it's off, there it's on. And now when we compare the two, we have a pretty good match. It's not perfect because, obviously I did it a little bit simply. Unlike the meters and feet thing, this is never going to be 100% perfect because of what's called metameric failure. But that really only comes into play at edge cases because you just saw the demo and it wasn't the brunt of the look. It would be a small outlier. So that's what I mean by a data collection machine, that we can not recalibrate the camera, but recalibrate our brain to think about the camera as just a data collection machine, and that we can push any one set of units to another. Once we do that, as we've done here, we've pushed both of these. Now both of these, even though this one was originally acquired on a 35mm film camera, and this one was originally captured with an Alexa digital camera, we could say they're now both log C ARRI wide gamut RGB. And by the way, I'm not doing an advertisement for ARRI here. Obviously, my whole point here is that these cameras are fairly interchangeable for the purposes of the photographic look. I'm not saying they're all the same as each other in other ways. For the purposes of the photographic look, they're all pretty interchangeable. So this just happens to be the Alexa. It could be a Red camera, Sony, any number of them. So that's the first step. So first we can push them both to be in the same units, and this is what I was calling in the demo uninterpreted image data, because now it still doesn't look right. This isn't the look that we're after. They're just in the same units. Then the look that we're after, we can just apply the same look to both, and they still look the same. So even though that look that we're after, I'm just turning it on and off. We're going to talk about that in a minute. Right now it's easy to apply, but it was a big deal for me to develop it. So we're just turning it on and off, and they look the same because they're coming from the same units and then going to the same units. Now I just want to, there's something this is vaguely off topic, but I want to bring it up and add a few minutes to this thing that I hope isn't much more than an hour. I just want to bring it up because I've had some people that are confused about it, and they bring it up when I talk about this, and I just want to show that it's not related, and it has to do with Bayer pattern and raw. And as I said, you know what, let me go back for one and do one more thing. I'm sorry. So back to this one. So just to make another example before we get to that Bayer pattern thing, if we're saying Alexa log C is meters and 5219 is feet, what about the crazometer that I was talking about? Well, what if we did something that we're actually told you should never do, which is bake a LUT in? We've all heard the horrible term bake. You're supposed to tremble in fear at the word bake. But let's say something that I'm not saying you should do, but with the Arri Alexa, you can put a LUT in the camera, and then you can actually record that as your actual master file, like not just send it to the monitor, but actually record the image with it baked in. And I've actually done this here. I didn't do it with the camera, I did it in post, but if you look up here at the top, if you, just in case you guys aren't familiar with Nuke, it's really simple. It's just each thing is a process, right? So it reads an image in, do something to it, do something to it, do something to it, view it. It's just a series of processes. Okay, so if we go to the top to see what it is that I'm actually looking at, this one is the camera original. You know, it's 2880 by 2160, not that that matters, but this is the camera original, uncompressed, Arri log C wide gamut RGB. This one already has the LUT baked in, and not only that, it's ProRes, it's compressed. I mean, it's not, ProRes is not heavy compression like H.264, but it is compression. So this has degrading image compression on it, and it's got the LUT baked in already, okay? Now, I've made an inverse of my LUT because, of course, like we were just talking about, you can take any, you know, if we've baked in a conversion from meters to feet or meters to crazometers, we can also reverse it. You just go the other direction. Just like you can do meters to feet, you can do feet to meters. So here I have a lookup table or a viewing transform that does the reverse. See, do you guys see what's happening in the processing chain here? The first thing now, instead of putting the look at the end, oops, I don't know what happened there. Instead of putting the look on at the end, where it started with log C, we've recorded a ProRes, that's a compressed file with the look baked into it. Then I put an inverse LUT on it, and now down here at the bottom, after it goes through the forward LUT again, let's compare the two. That's the difference. They look exactly the same. Now there are, of course, rounding errors because, let me turn off the LUT, because we were using compression, and also when you bake the LUT in, you're not maximizing your quantization allocation. So when we go in, you can see, do you guys see the pixels changing there? So of course there's rounding errors. Of course it's not perfect. Of course this is not the best way to do it. But you know, don't forget the sort of the perfect is the enemy of the good idiom, which is, you know, the fact that it's not perfect and that you can't do a perfect job doesn't mean you can't do a pretty good job, because I sometimes hear people say things like, well, you can't do that because that's not the right way, you know, like, you know, we can't make this look right because it's LUT baked or something. But if you do it right, you can do quite a good job. Now, even if the LUT, now my LUT doesn't do a lot of like clamping and clipping, it doesn't chop off highlights or lowlights or something, so they're all there to retrieve in the inverse. Now, even if you were to bake a much more destructive LUT than mine, even if you were, you could still invert it to some degree, but you would then be limited by the quality of the LUT, like that we've limited the image, and we're back to the very original thing I said, which is we're only limited by the quality. So even in that case where you did destroy it with a baked LUT, and to the point where you couldn't get the look you were after, you could say it's because you used a system that didn't get enough quality. You clipped information that you needed to make your look. And also just to exemplify that perfect is the enemy of the good thing, this is this is a graph of what we just did. So we're going, let's see. So this doesn't include the compression, the degradation from compression. It only includes the degradation from round tripping the LUT in extra time. We can see it's not perfect. You see what I mean? Like it's, so this is the original. Let me explain what this is, because I'm sure I'm not doing that very well at the moment. You know, this is just what a cube looks like. This is what all colors that you could possibly feed into the LUT look like. And then I'm reducing it down to this so we can see the part that almost every image is contained in this part of log C. There's almost nothing outside of it except for like car tail lights and stuff like that. So that's the bulk of the image. And we're going to compare what happens if you don't do anything to it to what if you round trip it through this, bake the LUT in, and then invert the LUT back out. And, we can see it's not perfect, but it's pretty darn good. And you saw perceptually how good it was. So it's possible to do things well even when it's not possible. The fact that you can't do something perfectly is not an excuse that you can't do it pretty darn well. Okay, so moving on to that Bayer thing that I started to say. So I think this should be obvious, but when we're talking about the part of the image data that we're talking about now, which is not resolution or anything like that, we're talking about tonal reproduction latitude. Like, do we get enough range from black to white? Do we get enough colors that aren't, saturation clamped and so forth? I've had people ask me, like, so do you need to shoot raw? And the answer is no. As we just saw, it doesn't matter what unit you're shooting in, you can do it. But I also just want to say raw is a very evocative English language adjective that evokes a lot of magic and sense of deep power. But the thing is, in imaging, the technical word raw, as opposed to the general English language adjective, literally just means it has not yet been converted from Bayer to RGB, which even though I've heard people think that they can get like more color information or something if it's not yet converted, this conversion is truly geometry and not nothing about color. Because in a Bayer pattern, at each pixel position in the image, we only have one piece of data. It's either red or green or blue, because on the camera, the photo sites at that position, there was only one photo site and it was only sensitive to one of the three colors. And in an RGB pattern, now this says viewing pattern, but it's not just viewing. It's also what we use over video signals, and it's in what's in almost every image file, unless the image file is called RAW. You have three pieces of information at each pixel position. So the piece of green image data right here, it's just this. We just move it over, right? Then the red one here, we just move it over. The blue one here, we just move it over. But we need to invent. See, there's some missing now. So we need to invent a red and blue one here. We need to invent a green and blue one here. So that's geometry. It's just filling in a little checkerboard hole. And I'm not saying it's not important. I'm just saying it's not part of the analysis of sort of the tonal and color information you've got. Because, so schematically, this is not what's literally going on with Bayer, because it's only in one channel, but schematically this is what's going on. You only have one color or another at each position. There's tonal variances. And when you zoom out, you see our ASC colleague Jaron Presant, anamorphically squeezed. And also the viewer's going crazy. And the reason the viewer's going crazy is because the viewer is doing a non-optimized resize right now as I zoom out, and it is not expecting a Bayer pattern. It's expecting RGB, so it's going crazy. But again, this is just schematically what's happening. That's not what literally happens with Bayer. It's just one channel. It's just a grayscale, and the computer or whoever is dealing with it knows what it means. We know, even though it doesn't look right anywhere, we know that whatever it is, this is green, this is green, this is red, this is blue data, and it knows it has to put that back together in this way. We have to adjust everything like this and fill in those holes. So as we fill in the holes, I have three different debayering algorithms here. These aren't the technical names for them, but I've called them poor, medium, and good. Okay, so if we go in, so the poor one, it's not smooth, and you can see artifacting from the original Bayer pattern. The medium one's already pretty darn good, and the good one's good. Okay, but when we zoom out, even that one, the poor one's a pretty darn poor, right? Like that actually looks terrible. But there's the poor one, poor, medium, high. So the difference really is just about geometry. It's about fine detail at edges. It's not about overall what we're holding in the highlights, because, of course, we know what we're holding. The green value here is the green value here. You haven't lost anything. All you've done is added a few extra pixels that are interpolated, not pixels, but channels that are interpolated. That's geometry. And just one, sorry to belabor this because I know this isn't the point, but there's been enough confusion on this that I do want to spend a few minutes on it. So the one last thing I want to say about it is the implementation of these de-Bayer algorithms. This happens to be Aries, but this is the same for all of them. Again, it doesn't matter, Red, Sony, whatever brand you like. This is not about brand allegiance. They provide an SDK. So in this case, Aerie has provided a developer's kit to Nuke. Nuke is a strategic partner with them, and Nuke implements Aerie's thing. This isn't something that the foundry who make Nuke, this isn't something they invented. They just implemented Aerie's stuff, so it's the same in every platform. Now, right here where it says de-Bayer mode, this is the only one that's actually changing that Bayer, that geometry. Right, so this is just their older legacy versions of it. That's the only one, and the sharpening thing, of course, is changing the geometry too. This stuff here is the only stuff that's actually changing the de-Bayer algorithm. They've very kindly given you the option to do some other math that you don't have to do at this step. But some people think, again, because of that word raw, they think if you do it here, it's magically better. But no. Exposure index, white balance, and tint, they're all the same thing. What are they? They're multiply the image in linear space. Color space, what is that? That's a combination of a tone curve and a matrix. That's it. You could do that stuff after the de-Bayer, and you wouldn't have, and it would be exactly the same. And the reason is, if you saw how each channel at each pixel is just a number, right? Like point 2. Well, we can see this one is 0.35, 0.768, right? 0.26. If I take this green information and put it here, and then I multiply 0.76 by 2, I'm going to get the exact same answer as if I first multiply 0.76 times 2 and then move it over here. And that's why Bayering is geometry and not like color subtlety. Okay, so sorry to belabor that one. Let's move on to the next section, which is, what do I mean when I say enough data? Well, we need enough data for whatever look we're trying to get, which could be various looks. So in the demo, I happen to be going for a traditional cinematic look, which on the one hand has lots of tonal information, lots of color information, but compared to some of the current formats, isn't especially high quality in terms of noise and resolution. It's still really, really, really good, but it's not quite up to some of the other contemporary formats. And both of these cameras got enough data in all of these areas to my mind anyway, to get that look either way. Because as you go through these sweeps here, you have color and intensity data all through the range. Both cameras, for example, when I get to, so this is 5 stops overexposed, but that means this gray patch is 5 stops overexposed. This patch here is about 1.5 stops above that, so this patch is 6.5 stops overexposed. So you can see, because the numbers are changing, you can see it's still getting a differentiation between 5.5 and 6.5 stops over. So it's holding all the way up to there. I've done these sweeps even to wider ranges before, but and I know both of these cameras get enough, but I just didn't do it this time. Same thing with the Alexa. You can see there's a differentiation as we go. There it's 8. It's point at 5.5 over. It's 0.88, and at 5.5 over, it's 0.95. So all we need is there to be a differentiation, because again, the machine will do the same thing every time, and we can convert meters to feet, and we can get these things to do the same thing, but we need the information. If we were shooting with another camera that had already hit its max before then we might not be able to push it to get the exact same look. But both of these cameras and all the stuff we've been talking about so far, which is mostly latitude or tones and color, get enough information. But what about noise? What about more spatial stuff rather than tonal stuff, such as noise and high frequency detail or resolution or whatever you want to call it. Well, both of these cameras got enough for this look that I was going for. These are the full quality, these are the full quality scans of the film and the full uncompressed, full size source for the Alexa. And you can see even when we go way in on it, you know, of course we're going to hit the end of its resolution because we have, you know, we have more pixels here than the thing ever really saw. And you can see even at fine edges, like the hair wisps there, these two are about the same as each other right now. You know, we can look at that on another shot. Like, let's look at, you know, if we go way in, you know, this is how wide the shot is. So we're looking at a small detail to examine how much fine information it has in a very small localized area. Sorry, it's the computer's slowing down a little. And we can see it's pretty similar. It's not like, you know, like where it breaks down is about the same. You know, we can see the eyelashes, but they're not like tack sharp in terms of where the edges of them are, which is to be expected when it's, you know, you're zooming that far into an image. So they're about the same for that, which was enough for this particular look that I was going for here. But what if we were going for a different look? What if instead of a traditional film print look, what if I was going for a slightly cleaner, more contemporary look? Maybe I still wanted these colors, but I didn't want the grain, and also besides that, there's also film has edge halation, which means, so film, when you have a high contrast edge on film, the light goes through the emulsion and exposes it like you'd expect, but then it hits the base, the back of the film, bounces back with unfocused light and causes a blur edge. So when you have high contrast edges, which is actually where we can see edges the clearest, you have this erosion from film. Now that was the look that I wanted for this. So on the Alexa, I've got my own algorithm that just puts that on. This isn't me going in and painting it. It's an algorithm that was pre-designed, and you just plop it on and it does it. So if we wanted a different look, the problem, if we wanted a cleaner look, only one of these cameras has enough information for it. Because if this is the look we want, still the same colors, but if we like this cleaner edges that don't have halation and lower noise, it's not, you know, no camera in the world has zero noise, but much lower noise, the Alexa can do that look, but actually film wouldn't be enough information for that. Because these edges are already eroded, we never got the information, we can't get it back. And noise is, although noise perceptually looks like it's something on top of the image, it's not something on top, it's lack of information about the image. So that's information we never got. Even if you put a denoise algorithm on, that's just a way to cover up the fact that you don't have information. When we degrade something, you can degrade it for real, but if you want information about what was actually in front of the camera that you didn't get, you know, you can fake it, but you don't really have it. And I actually here have, is this it? Yeah, this is one version. I mean, there's so many different versions, but this is one version of a professional, not some crummy thing. This is one of many versions of a denoise algorithm on the film. And you can see that it actually makes, it just turns the lack of information into a different kind of lack of information. We now have weird, gritty, see how this looks like it's affected and sort of more electronic as compared to that. So obviously there's different ones and you could probably tune it a little better than this. But if you didn't get the information, that's the one thing that you can't do something about. All this stuff I'm talking about, you can convert meters to feet, but if you didn't take a measurement at all, or if you were off the end of your ruler, you can't get that back by converting between meters and feet. And you could extrapolate this into other situations. So if you want to imagine a wider situation where we would accept even more cameras, what if you were making something where for your look you either wanted or were okay with obvious rolling shutter artifacts from a camera that has a really slow shutter chase, or you were okay with big giant macro blocking from compression. I don't like that look, and that was not a camera that did that would not be acceptable for this. But if your look, if for your look you wanted that, that would open up a lot of like some of the more consumer level cameras. And furthermore, if that was the look you were really after, if you were going to do that to the Alexa or to the film, you would have to also create your algorithms for that. You'd have to either actually compress it to create the blocks or create an algorithm that mimic the blocks and so forth. Or what about the other direction? What if your idea for a look is you're going to show something in an IMAX cinema and you want it to feel really resolute even to the person in the front row? Well, these images are fine for any, we know this amount of resolution here is fine for any normal cinema, even like the Cinerama Dome or something. But when you talk about IMAX, you're actually looking very closely at a small sliver of the image. I'm sure these cameras would both be fine in IMAX, but if you really wanted, if your whole point was somebody sitting close in IMAX theater really sees a lot of resolution, maybe neither of these cameras is fine. Maybe you need to shoot 15 perf 65 millimeter film or Alexa 65 or something like that. Okay, moving on to the next section. I just want to talk about the scale of the attributes. When is something, because I'm saying, look, there can be some outliers and you still have the same overall look. So I just kind of want to put things in perspective of scope, because like I'm saying, as I said in the demo, I'm not talking about forensic details that we can see when we actually compare them side by side. We're intelligent enough to say, I can see that, but it's a forensic detail. When the audience, looks at the image and they don't have a comparison, this is not something that matters to my overall look. So as we compare, maybe, are we getting tired of this shot? Maybe I should go to a different one. I don't know which one. Let's see, this one has skin tones and stuff. Okay, so as we go between film and digital with the film, with all my display prep stuff on it, we can see, look, there's very, very slight changes. For this point, it's good to not look at the exteriors, because obviously we had shifting light on the exteriors. You can say, oh, there's a tiny, tiny, tiny difference in skin tone, but to me, that's not really a change in what I would call the photographic look, because if you saw one without the other, you wouldn't know, or if it was a cutback, you wouldn't know, which I personally consider the gold standard for cinema. If I do this shot and then cut away to somebody else, if I do this shot on film, I cut away to somebody else and I cut back to it on the Alexa and you don't know something changed, I feel like we've met the gold standard. But to me, what does look like a different look is that. So that's using Aries out of the box look, their K1S1 look. We still have my other stuff, the spatial stuff, grain and halation and all that. But this is just all the color rendition. They still look like each other, but it's a totally different look. Let's look at it on something else. So again, they look like each other. There's film, Alexa. Wait, I don't even know which one's which. That's film, okay. So film, Alexa, they look like each other, but that is a totally different look to me, to my taste, than, oops, what happened? Oh, there we go. Than that. And this is what I mean by display prep. I mean, this is kind of the crux of the whole thing. To me, these two are the same look. That's two cameras, not with the same transformations applied to them, but with equivalent transformations applied to get the same result. That's two cameras, and then we go to we do something different in the pipeline instead of changing out which camera brand we're shooting with, and they still match. And I'm not doing a bunch of different stuff. Like, how in the demo I even said, like, there's, I did the very simple color grade and stuff. This is literally just changing the lookup table the final color transformation on both of them together. So they still match, even in this totally different look, they still match each other, but it's a totally different look to me. Now I'm going to take this same concept even a step further and say, okay, what if we tried to match those same two? We're now looking at the exact same thing we just were, except I've turned off the grain inhalation. That's the only difference. Okay, so there's my viewing transformation. There's the out-of-the-box airy one. And by the way, I'm not saying this to disparage their look. It's just two different looks. And if I tried to match the two of them with lift gamma gain, which even the lift gamma gain is not the only thing in a color corrector, but that's usually what gets used for real in-color correction, we get something like this. That's still pretty different. And not only that, you now actually see, by making them more similar, I've actually shown how different these actual looks are. Because when you do an overall match, then you start to see the subtle things that aren't the same. You can't say, hey, one needs to be bluer, or one needs to be warmer, or one needs to be contrastier, or one needs to be more saturated. They're just different. And part of the reason for that in this case, only part of the reason, is lift gamma gain is very simple. Now, I showed you that to match these two, just tones, right, just densities and not color, we needed a funny, crazy, wavy line like that, right? But here's what lift gamma gain does. This is all it does. Let me reset these for a sec. Let me just get a new one. They do the same thing in every color corrector. So gain is multiply, so it stays a straight line and it goes up and down. Gamma is an exponent. Oops, sorry, that's lift, sorry. Gamma is an exponent, so it just bends. It leaves black and white tethered where they are, and it bends the image. And if you don't think that's limited enough already, guess what lift is? It's also multiply, but with the pivot at the top instead of the pivot at the bottom. So you can't do very much with that. I'm not saying you can't do other stuff. I'm not saying it's impossible to do other stuff in color correctors, but by and large, that's what people tend to actually use. But let's just say, what if I did match these? What if I did, and I've just done this in advance, what if I found the funny wavy lines that I need to perfectly match these in densities? Because we said there's tones and densities, but there's also colors, right? Now if I match the two in densities, in a way we have a better match, but it shows off even more the complex differences. That's not simple at all. It's not even like, it's not saturation, it's not an overall color thing. It's just certain color renditions. And just to show you that I really have matched these in tone, if I make the image black and white, they match perfectly. So I really have matched the tones, the exposure, the tone curve, whatever you want to call it. But the colors are still that different, and you see how complex it is. Like almost, like you look at his eyes, and it almost looks like something's going on with the focus. It's so complicated what's going on, but it's just color change. Okay, moving on. Okay, getting into the home stretch here. So a lot of people ask me, okay, that all sounds great, Steve, but what can I do if I don't know math and programming? This all sounds very overwhelming. It's really cool, but what can I do? So the number one thing is just change how we talk about it, change our myth and our paradigm, because it's so ingrained in the professional imaging culture that the camera makes the look. It's our figurative paintbrush. We test cameras for the look that they create. We don't test them to see if they get enough information for us to make a look in the pipeline. And in fact, if we're testing them for a look, that means we're not even separating out variables to know whether we can make a look later in the pipeline. And I've also seen it happen where, it's kind of that collective ignorance thing where everybody's saying something, so you feel like you should say it too. Because I've seen, interactions where somebody that's maybe even a very accomplished, impressive filmmaker is saying some of this this camera just makes this look kind of thing to another very accomplished filmmaker, and the other filmmaker's being nice, but it's kind of like, yeah, but isn't that really just sort of a religious myth? And instead of buying in and going for the peer pressure, and the response is, yeah, that's true. So if we actually push back on this and change the storyline, we can change how, vendors and collaborators and everybody we work with thinks about this stuff, and it can change the whole ecosystem. You don't have to do everything by yourself. Another thing we can do is perceptual identification. So even if you don't know how to do the algorithm, like I've literally written, my own algorithms from scratch where I'm writing code. I'm not using any off-the-shelf plugins. I'm really saying the math of I want this pixel to be transformed that way. But you don't need to do that to really get involved, because if you can start to recognize, as I said in the demo, the building blocks of what makes the image, you can start thinking about reassembling them in different ways. And the example was I was showing you the halation, and that's a pretty great example, because I think there's plenty, and I could be wrong, but I think there are plenty of accomplished filmmakers who, let's turn the grain back on. And so what the halation looked like on this shot, for example, is that. Okay, and I think there's plenty of accomplished filmmakers who they might see this whole shot or the other or the film, it doesn't matter which one which, and say, I like that look. How do I get that look? And then they might say, oh, you know what? I like how this flare looks. Let me get that brand of lens. But the thing is, if we start isolating our variables, you don't have to know yourself how to write the algorithm. I wrote this algorithm myself, but you don't have to. You don't have to know how to write this halation algorithm. But if you know that this look is from film halation and not from a lens model, that's very powerful right there. And we know for sure it's not from the lens because I shot the same lens on both formats. We know it's from the, we know, what's going on here? Why isn't this, oh, sorry. There's the film, which of course does not have a halation emulation algorithm on it. And, there's the Alexa without the halation, and there it is with. So this is just an example. There's all kinds of things like this where sometimes we have a tendency to guess what caused something. Like, I like the look of this film stock because it was saturated, but maybe it wasn't saturated. Maybe it rendered colors weird. Because one thing I've noticed is when colors are rendered off, like if greens come out cyan and reds come out yellow, that might feel saturated, but it's not really technically saturated. If we can start to figure out what some of these building blocks are, we can talk with people that we work with, whether it's colorists, color scientists at facilities, various vendors, and so forth. Another thing we can do is, again, remember that the difference between a developer and user is not the same as the difference between an author and a shopper. So one thing is, I do all this work, and sometimes people think, my God, it's so complicated the way you shoot. And I'm like, no, I'm a DP and I do this stuff, but they're not really exactly the same thing. Because I do all this work kind of on my spare time, then when I shoot, it's really simple because I switch hats from being a developer to being a user. And when I use this stuff, it's all really simple. I think all my workflows are much simpler and more streamlined and more confident than a lot of other projects. It's not more complicated just because I did some complicated development. And the thing is, even for me, I'm literally doing both things to an extent. It's still separated. First I do the development, then I'm a user. So that shows that you can get involved in the development without yourself necessarily having to write code or do math and all that. You can partner with people or push vendors of all kinds, whether it's software people, whether it's your post-house partners, whatever, to investigate this stuff further. And as I say here, we can push for new spaces in the marketplace, potentially. I do just want to quickly go through, and I know everybody's getting restless. We're almost done. I just want to talk about for the people that are interested in looking under the hood like that, and the sort of, because I know there's people here that'll be the opposite of this, but what can I do if I don't know math and programming? I know there's going to be some people that are like, how can I learn this stuff? And obviously that's way beyond the scope of this, but I just wanted to talk about it for a couple minutes and say, firstly, one thing to remember is there's the data sets on the one hand, like the actual collection of data, and the computational tools, what you do with the data, are two sides of a coin. You can't belittle one or the other. I mean, I've heard people say, I shot all these data sets on film, therefore I have a film look. It's like, but what did you do with the data that you shot? And so both things are very important. Or I've heard somebody, a claim of, this has some really cool math in it. It's like, yeah, but what are you doing? And in my case, I needed really specific data sets to get that print film look, which included me, actually printing film and getting the data with densitometers. Because if you just scan it, you don't, that's scanned film, not print film. But even if you're not going for that look, and you don't need strong data sets for the look like that, you would still need data sets to match cameras, as we've done here. If you have different cameras in a show and they're supposed to give you the same look, you need to match them. And also, even if you're just going to do a fun look, like obviously my look was very rigorously set up to look like at least a version of printed film. But even if you're just doing some fun look, you would still need a data set in the sense that you may not need a whole bunch of experimental data of measured colors, but you would still need a broad sampling of images to look at your transformation on. And that in itself is a data set. Because, for example, you might be doing something really harsh in the grade and you don't realize, and if you don't have you don't have something bright red in the shot you're working on, and then you put your transformation onto a shot that has like a car tail light or a red LED and it all breaks or something. So even just having a lot of shots is a data set. So I just want to, and with both data sets and computational tools, the other thing to remember is you have to actually get it right. Like I've seen so many people say, or at least now and then say, the math didn't work, so we did it by eye. And it's like, well, math works, you just didn't do the math right. So, I mean, even things that are really simple, like scaling images, I've seen that happen with. And so the thing is to keep pushing farther with both the data sets and with the computational tools. Like I've never been finished with this stuff. I'm always tinkering and refining. It's like, how can this be better? If you're trying to look for an end and say, once I do this, that's it, and I don't want to hear what's wrong with it, you're bound to have something wrong. Just figure when you start, there's 100 things wrong, and by the time you think you're finished, there's only 20 things wrong. But I just really quickly wanted to show some of the types of things that I'm doing because I get asked that a lot too. So one example is, here is a data set that's got thousands. This is an actual photograph data set. It's just plotted in 3D space, where I have thousands of data points for both Arri Alexa and scanned film. So this isn't print film. My print film data sets, I can't have thousands like this because I don't quite have a way to automate it like that. So I do have print film data sets, obviously, but they're sparser. But I can graph them. So this is just one of many data sets where I did a lot of work to make sure that they were rigorously figured out. And if you're matching two cameras, you either need to shoot them at the exact same time in the same circumstance with the same lens and the same chart, or you need your experiment to be so experimentally well defined that you can actually repeat the exact same color of light and intensities and all that later when you don't have a side-by-side camera. Here's tetrahedral interpolation, which is the thing that I showed you that we did the quick match with. I don't really usually use this when I'm actually building a LUT like that for two cameras. I have at times, but I don't usually anymore. But so again, this is me kind of in a fun way implementing math that exists. I didn't invent the math, but I sort of invented this implementation of it, where it's tetrahedral interpolation, and you can grab a corner. So here's just moving red around. See that? And it's smoothly, everything stays pretty rectilinear, but I can grab the red corner, I can grab the blue corner, and that's some three-dimensional math that's attacking stuff that you can't do with 1D tone maps, as we were looking at. Another example of a thing that I do that's like my idiosyncratic little fun thing is I created it's kind of a custom color space where I transform it into what I call cone coordinates. And then once I'm in that color space, I can do slightly odd complex things. Like, for example, like that word saturation, again, there's an infinite number of things that will perceptually look like saturation to humans, but the saturation knob on a color corrector only does one really narrow thing. And actually, let me show you that first. This is what, so again, this is the gray diagonal part of a cube. It's just so we can look at the, the part that has most of the image in it. There's the whole cube. Most images are contained in a cylinder in the middle like that. And what the saturation knob on a color corrector does is, of course, it just blows it all up around. If we look, now we're looking straight down the gray diagonal. It just stretches all the colors linearly away from the gray diagonal. Let's just look at that on the whole thing. So the gray diagonal stays where it is. Oops. Gray diagonal stays where it is, and everything rectilinearly stretches away, which means, of course, by the time a lot of times we're worried about skin tones, which are in the middle, but by the time we've had more than a little effect on skin tones, the outside is exploding like crazy. So I have this different kind of saturation that happens in cone coordinates, which is over here, that looks like that. See how that's different? Now, when a lot happens in the middle, not a lot happens out in the sat. So when we saturate skin tones and all of the middle of the image, we're not exploding our other saturated colors like fire trucks and safety vests and stuff like that. And not only that, also see how it's got curvature to it. It's not all rectilinear like the other saturation. I also have a version of that right here where you can target individual colors instead of doing everything. Ooh, got to turn it on. So like here's the red, just the red saturation without the other colors. And then I have another thing here where we can transform hues, various colors. We're adjusting various colors within the cube to, like, cyan can go more green, or red can go more yellow or whatever. And again, the usual way that it's done, I'm not saying it's the only way it's done or the only way it can be done, but in most actual implementation today, when we need different hues, people usually only use 3x3 matrices, which this is all a 3x3 matrix can do. It can stretch and it can skew. And that's it. So successive skewings can be a rotation, but really everything stays rectilinear in a 3x3 matrix. So that's a much simpler way to move colors around. So you can see you can keep playing with it and refining. You can see we got a pretty great 3D match with just tetra, but in my own learning process, it took me a while to get to tetra, and now I'm beyond that, and the stuff that I might use now is a little too complicated to get into here. Anyway, that's about it. So I just hope this is an inspiration to think about how can we author these looks in the pipeline, and another thing it can really help us with is, and I just want to go back to this one. This one. This one was really important. This is the one where I said, what if we match, what if we match my look to Aries only with 1D but not with 3D effects? And this is the kind of thing because when you start isolating variables and you say, okay, we've matched the tone map, now what's different? And that's how we can start evaluating cameras better, because right now, when the myth is the camera makes the look, what's happening is we get what the camera does plus some out of the box pipeline that nobody told us what it is, and then we compare those two things, and we've compared the camera and the pipeline together instead of one and then the other. And the better way to do it is say, when we don't say, hey, it came out different, that's how it's different. We just say it came out different. When we push it back to being the same, what's left? What's still different? And that's why you can say, like I've heard people say, one camera has better highlight, quote, handling, which I don't agree with. You either got the highlights or you didn't, and then the handling of them is done in post. If you don't like the roll off because it doesn't have a long shoulder, guess what? Draw a curve that has a long shoulder. But what you can't change is the information you actually got. So let's just make a hypothetical example. If you were going for a traditional cinematic look like this, you don't have to, but if that was your look, but you had to shoot with one of two digital cameras, and for some reason somebody said you got to shoot with one of these two cameras, you can't use film and you have to use one of these two, not even a different one. If one of them had an out of the box look, just the look that was filmy to your taste, and the other one had a very garish electronic look, and you just picked it based on that, you're not evaluating the stuff that's actually different about the camera, because as we can see, we can push one look to another. Maybe the one that had this more cinematic look out of the box, maybe it's not getting those highlights you need, or the shadows, or it's too noisy, or maybe it's got a slow chase on its rolling shutter. Those are technical differences. We can push the shoulder to be the same on either one. So hopefully this is, I just want to get the discussion going and hopefully inspire people to think about how we author in the pipeline and how we evaluate cameras for attributes that really are important, because cameras really are different and not the same as each other. I just don't think it's about the aesthetic photographic rendering that's different. All right, any questions? All right, thank you guys. Thanks so much.